Hello community and welcome back. So today, before going into other areas of the engine or starting to go into the core areas of the engine more specifically, I think it would be good to discuss memory allocation, because many things that you're going to be seeing in the core area of the engine take some decisions regarding to how memory is allocated and managed. And without an understanding of what the theory or what the idea of this is behind, it's going to be difficult to go into them and explain how they work. So I prepared this special presentation today for explaining how memory is managed and many of the decisions behind how that works. So without any other thing to say, let's begin with this today. So we know that Godot has its own memalloc and memnew. We'll see this later. We do this because we can customize memory allocation better. We can track memory allocation if we just use the system versions of malloc and new. There's no way to track anything, so we use our own memalloc and memnew, which are like analogous to the operating system one, and we can track whatever is going on. These are in core memory.memoryh file. We're going to see this later on in subsequent episodes, but for today, just at least good to have this covered. So let's talk about memory. We have a fixed and a limited amount of memory. We know it's hardware. We know it contains bytes. Imagine memory as this grid of empty cells. Imagine these are bytes. This little square are bytes or whatever. And this represents what we have in the memory DIM you have below. So programs normally allocate memory randomly. You could say randomly, but in the sense that you don't really know what they do when you call malloc and free. Just imagine it's randomly. It has logic, it's complex, but just say it's randomly. Allocations can take any amount of bytes. They often happen in something called the heap. There's also the stack, but I think if you are trying to understand how Godot works, you understand what the stack is, I suppose. Otherwise, you can go read it up. But yeah, allocation happens on the heap for the most part when you call malloc, free, new, delete, and these kind of things in C++. Remember that these allocations return a pointer, and the pointer can't be moved. This is just a pointer. So allocations are these things that you call alloc, new, whatever, returns a pointer. You can do anything you want with the pointer. You can't really move that pointer because you have to use that pointer to later on free that memory, right? So this thing called the heap is memory that generally grows, starts from some memory position, and the more you allocate, the more heap you use. You could say that it grows in a direction because you allocate something tiny, then something big, then something tiny. And then you can free things randomly and create holes. And every time you create a new allocation, the allocator is not really going to always put things at the end. If there's any hole in the middle of the allocations that you have made so far, it's going to try to use that instead of just trying to put things at the end of the heap. Because then you can not grow infinitely every time you do a new allocation. So the thing is that the more you allocate, the more holes happen in general, and the more the holes are reused when you do new allocations. And that's how it works. So what is fragmentation? Well, the thing is that you may have a certain amount of memory free if you count the white squares here, but you may want to allocate something that there is not really, how can I say, in no contiguous memory for it, just not memory contiguous, like one byte of the other that you want. So that means that that hole remains there, and then it has to be allocated at the end. And then memory keeps growing and growing until it reaches a very, very big memory usage. Or if you have a limited memory amount, like some platforms have a limited amount of memory, they don't have a swap or anything like that, then that you're just out of memory, which is what happens when you have enough memory in bytes free, but you don't have enough contiguous memory to do the allocation we want. That means you're out of memory, even if technically you have enough memory for that. And this is a problem because you're just out of memory and your program is going to crash for the most part. So how do we avoid this? Like you have fragmentations, then you have holes, and then you have enough memory, but everything is too fragmented, so you can't do the big allocations anymore. So how do we solve this? Normally, what applications or game engines do is they split the large and small allocations. If you just care about the small allocations, like smaller than 16K or something like that, you can leave a percentage of your whole heap free, and you're never going to have like enough fragmentation that is going to cause out of memory. If you know your memory is not going to go over the threshold that your game uses, but you leave a certain percent of memory free in your heap or your max heap, you could say, you're not going to run out of memory if you're only using small allocations for that heap. Like there's a relationship between the size of the heap, the percent of the heap you leave free just for fragmentation, and the amount of memory you have that is going to just make it really difficult that you get out of memory due to fragmentation. So this is how you normally handle the small allocations and how you avoid these situations from happening. So what do you do with the large allocations? Okay, one typical strategy, Godot 3 uses something called pooled memory. This means that you have a large amount of memory that is reserved for pooled memory. You allocate anything in there, you just do any large allocation into the pooled memory, and you have to lock the memory when you want to use it. The reason you have to lock it, it's going to make sense very soon, but the idea is that you have to lock the memory before using it. So if you're out of memory, if you have the amount of memory that you need free but it's fragmented, then the pool is going to compact, and because the handles to these memories are like a pointer to a pointer, you just can't compact and it's okay. And if you're still using the memory, it means you have it locked, so it's going to be able to not compact the block that you're using, or it's going to wait until you're done using it until it's done the compacting. This is how Godot 3 works, and it's okay, and that's fine. But we now have 64 bits virtual memory. What does that mean? So nowadays, you know that every CPU that you use in your phone, in your game console, in your desktop PC, everything is 64 bits now. This means that you have something called 64 bits virtual address space. What is this? Let's discuss this a bit more. So when you run something in your operating system, you have something called the virtual address space, and you have the physical address space. The physical address space maps to your actual, like your DIMM memory, your chip, physical thing. Like you have 32 gigabytes of RAM. The physical address space is any address inside of that chip, pretty much. But the virtual address space is something entirely different. It means that you have like terabytes and thousands of terabytes of memory, but you can't really use it all. But you can like decide where your physical memory maps to your virtual memory. You can put chunks of physical memory mapped to any address of the virtual address space. And this is very, very useful. At the beginning, you may be wondering, like, what's the deal with this? The thing is that the virtual address space is so much bigger than the physical address space. Just imagine that your memory is the size of a house, then your virtual memory is the size of the solar system. That means that the address space that you can map with the virtual memory is absolutely huge. So what happens here is that normally modern allocators in 64-bit CPUs, they will just have the heap for small allocators at the beginning of the virtual address space, and they will have the large allocations at the end of the virtual address space. That means that because the large allocations use pages, remember the pages are like the virtual memory is mapped in something called pages, which means that every 4K or something like that, depends on the operating system. Often it's just 4K. You can map pages anywhere in the virtual address space. So because the large allocations are just allocated in pages, you can have as many as you want in the end of the virtual address space, and you can put them anywhere. So you're not really going to have any fragmentation. And this is really important because it means that nowadays there's not really any problem with fragmentation in modern operating systems thanks to 64-bit address space. So you have been rickrolled. This was never a problem. We discussed it, but it wasn't a problem. But it's good that you know that fragmentation is not really a problem nowadays, thanks to 64 bits address spaces. So you don't have to worry about that. You just can use the memory more like indiscriminately, use the heap when you need, use the larger locations when you need, and it's going to be fine. You're not going to have any problem with fragmentation. So it's good that you know this, because the engine, especially Godot 4, is designed around this. And you're going to see it very much when we discuss the source code further ahead. But performance is still a problem. You know, like we have the heap and it's not a problem, but performance is still a problem. So how you manage memory can greatly impact performance. So it's never that easy. So sorry, it's just never that easy. So how about, well, when you call malloc new free delete, just extremely inefficient. It's very slow. It has to look for memory holes. It just takes a very long time to find the memory. And if you're writing critical code, it's going to be very inefficient. It's going to make your game very slow. So this is one problem. The other problem is that allocating and accessing memory that is very sparse, like all over the place, in the virtual memory or whatever, is going to be very cache inefficient. This means that you're just reading memory from all over the place, and this is just very, very slow. So one thing that is very important to understand regarding why we care about memory performance nowadays, the reality is that in the past 15 years, the RAM speed maybe increased by 3, maybe 1,000 megahertz or something like that to 3,000 megahertz. But at the same time, the amount of cores in a CPU has increased like 16. This means you had like single core CPUs 15 years ago. Now you have 16 cores. And this is really a problem, because you have a lot of cores fighting for RAM access, and the RAM access is not much faster than it used to be before. This is really a problem. So let's begin by explaining how the modern caching system works on CPUs. So you have your global memory. Your global memory can be dozens of gigabytes, usually 32, 64, whatever. And accessing takes around 60 to 100 nanoseconds. That's just a reference number. It's going to change, maybe not be exact, but just you get an idea so the relationships between the different cache levels are. So then per every CPU, not CPU core, CPU. You know, you have systems that can have multiple CPUs installed. In this case, every CPU has L3 cache. The L3 cache is very large. It's the dozens to hundreds of megabytes. Like the high-end CPUs can have like 200 megabytes of cache. It's incredible. And it's much, much faster than the regular RAM, because it's just right there in the CPU. Maybe taking 10 to 15 nanoseconds to access, which is much faster than the actual RAM. Then for every CPU core, what you have is the L1 and L2 cache. The L2 is a more general purpose cache. It's hundreds of kilobytes, it's usually like 256 or at much 500 kilobytes in very high-end CPUs. And it's much faster to access. It's like 3 to 5 nanoseconds to access. And finally, you have the L1, which is not exactly the same thing depending on the CPU. Some split instructions and code, or have it mixed. But this is very, very fast. It's 1 nanosecond to access, but it's very tiny. You have to understand that it's a very, very, very tiny cache. So what are cache lines? So when you read something from the regular RAM, even if you access 1 byte, every access is going to be 64 bytes, which is typically in every CPU what's called the cache line. So if your memory is all sparse and all like around the place, every time you access one element of your scattered memory, it's going to read 64 bytes, not 1 or 4 or 8. So you have to be very careful when you read memory. You try to organize at least everything in the size of a cache line is going to be helping you a lot. So again, avoid tiny scattered allocs on the heap. That's going to increase your performance, because when you read something from the memory, it's going to do it in a full cache line. So what are pages and what is TLB? So as we discussed before, you have something called the virtual address space. The virtual address space is mapped to the physical address space. Well, actually it's the opposite, but it's using pages. often 4 kilobytes. So when you read something, it's not really going to read like a page of into the memory, but you have to take in consideration that all this mapping from virtual to physical is done in something called the TLV on the CPU. And this also is a specific memory inside of the CPU that contains entries mapping like virtual pages to physical pages. And if your memory is very scattered around, like not in pages, then the CPU is going to have to load more like references to where the pages are located all the time from the main memory or the caches, depending on the CPU, but it's still very slow. So having your memory at least optimized around 4K pages is very optimal, because then the CPU has to do much less loading of where the actual pages are pointing from the virtual to the physical address space. This is really good to understand, because it's not that when you do a read of memory, it's going to it's not going to fetch a whole page, but it's going to have to like fetch where that page is pointing to, and this is very important. So if you try to get everything as much as possible grouped into pages, then you're going to have much better performance. So yeah, that's it. So how do you optimize for L1 cache? You have to think that L1 memory is very tiny, just a few kilobytes in general. So you optimize for very basic algorithms if you want to make them the best possible use for the L1. So it's going to mostly benefit from sequential memory reads and writes, like very simple algorithms that just read a lot of memory, write a lot of memory, just do it by bit. So some bits are being read, some bits are being written, all in sequential memory. If you don't use sequential memory, well, at least try to align to cache lines, like 64 bytes. So again, the working memory is very tiny in L1. So if you want to like have conditionals that just go somewhere else, or just go and do something when something you're processing meets some condition, you can't really do very complex things. You just can go and execute or call if you call a function, most likely your L1 is going to be flashed and it's going to have to be like reloaded when it returns from the function. So don't do any really complex logic. You can see here in the Pacman, just one thing after the other. Don't do anything complex. That's very L1 friendly. Don't just go into like complex code paths like you're seeing in the bottom in DigDag. Just don't do that. Just do like the Pacman, one after the other, like munch data in, munch data out. Just very easy to optimize for L1 if you do this. So how you optimize for L2? This is more interesting. I think this is one thing that you're not going to find a lot of bibliography around, because most authors just tell you how to optimize for L1. If you read about ECS and that kind of thing, this is mostly all L1 optimizations. It's nice, it's useful, it's cool, but in the real life, these kind of optimizations are only for like very specific types of code, not for all your whole game or whole engine. So I think it's interesting that you have to think that L2 is like the biggest cache level per CPU core. You have to think that if you're going to have more complex algorithms that do, I don't know, hash maps or things that are just in generally more complex, that require more logic, decoding of stuff, uncompressing, just more complex code in general, it's very important to know that the L2 sizes, you can think like 128 kilobytes, kind of standard L2 nowadays. So make sure that your working memory for your algorithms is around that, like per batch. You're just going to be processing in batches always anyway. So if you can keep your algorithms to 128 kilobytes, just going to be really efficient, and you're going to be keeping it inside of L2. And as we have seen before, the latency for L2 is still very good. It's like, I don't know, 3 to 4 nanoseconds. It's still really fast to have something in L2. So if you can keep your like algorithms there, they are not something like very linear like the ones in L1, but they can have more conditionals and things like that. It's fine. Like as an example, if you have a script VM has like runs a loop with instructions and does things, this is ideal for L2, because if you can keep your whole VM inside of L2, it's going to be really fast. If you make a really huge VM, then it's going to have to be running at L3 speed, which is like slower. So any kind of things that you have like data processing that is more complex, as I said, like data decompressing, resource loading, this kind of more complicated things, you have to make sure that it's still relatively small, so it takes advantage of L2. Again, remember that all this comes in cage lines, so you always have to work like thinking your algorithms are in cage line size. So finally, L3 is the global like per CPU cage. It's shared among all the cores. So what exactly do you optimize for L3? This is something that you won't find a lot mentioned. But ideally, what you want to do for L3 is make sure that everything that you're going to be processing every frame in your game, at least as most as possible, fits inside of L3. Like the basic of your scene, game engine, whatever, what's going to be accessed every frame, make sure it can fit in L3. This is not that difficult to do nowadays because it's megabytes, like even hundreds of megabytes, like modern CPUs have that much L3. So normally in game engines, you have to make sure that your data is very packed. Even if it's a lot, make sure it's packed so it can fit inside of L3. Like use pool allocators, put things together, make sure that things are all inside of the L3 by packing data as much as possible. And don't do scatter allocations of unrelated stuff all around the engine. Okay, so next. So again, cage usage in real life. Again, remember only a small part of your game code is going to benefit from L1 optimization, like maybe 5%. This is why when you see people telling you should make a ECS-based architectures, all very like memory coherent, so you can process everything sequentially and everything. It's like, I mean, sure, but it's just a few parts of your game that needs this kind of optimizations. Normally in a modern game engine, these things are handled by the game engine. You don't really have to get into that complexity because your game logic is going to be more event-based in most cases. So this is good if you want to do custom optimization on your own and things like that. But normally, users don't really care about this kind of optimization when making the game, except in some cases where, I don't know, they have these simulation things where you have like a grid and lots of things are simulated. Okay, that's okay. Then you need like proper L1 optimization for that kind of game, like city simulator. Maybe you have that. That's fine. You have like 10,000 entities. Okay, you need L1 optimizations to make them fast. That's fine. But most cases, it's not needed. It's something that it's something that you need to understand that in most cases, it's a very specific like corner case optimization that you are not going to need. It's more interesting to understand that it's better to focus on making sure that your game is well optimized, your engine is well optimized for L2, because that means that your algorithms are using like all data very packed, very efficiently, even if it's random access, so it can fit inside of L2. And of course that the game engine packs everything nicely, so you can fit everything that is the working memory for the frame in L3. This is a real important thing to understand when you have to understand cage usage for memory. So you're going to see that Godot does this a lot. So some typical memory strategies, just very basic things that you're going to see when we discuss the source code, but so you understand what it is for. So growth only allocation is a super important to understand memory strategy. This is used a lot because devices now have so much memory and you don't really need to use 100% of it, especially the CPU memory. So it's better to just like leave memory, you could say, unused, but that is going to give you a lot more performance. How does this work? Well, use growth only allocation. This makes sure that you are using growth only data containers like the arrays, the hash maps, page allocators, the RID owners. Well, we're going to see what these are later, but generally what Godot does is uses containers that if they are tiny, they are tiny. If they grow, then the capacity increases. But if you remove elements, then the capacity doesn't really shrink. The capacity just stays there. It's like a worst case allocation strategy because as much capacity you use is going to remain like that for the rest of your game. You may like unload the level, but a lot of the capacity allocated for different things in the engine are going to remain like that. So this ensures that very few actual allocations. This makes sure that you allocate very little because the allocation is on the heap. It's only done when you grow the capacity. But then any time else that you need to get memory, you just use the containers, the container memory that is already allocated. So it's super fast to allocate stuff and remove memory. The other really nice thing about growth only allocation is that the memory is very contiguous. Anything you're using is going to be mostly contiguous. Okay, you can free stuff and you're going to have holes. That's okay, that's normal. But in most cases, when you're working on games, what happens is that you're going to be allocating a lot of things together and freeing a lot of things together that are related. So in those cases, when you use this kind of growth-only allocation, those are going to be all packed together in memory and going to be freed. So you're going to have really little, like, there's no fragmentation here again, because this is allocations of like same size things. All these containers use like same size things, so there's no fragmentation. But you can have scattered memory and holes, that's okay. But normally what happens, as I said, is that you just allocate batches of things together in the normal lifetime of your game. So normally things just go together, load together to the pages. They go together as lines. They go just to the same areas of the cage. So it's very efficient. And again, there's no real fragmentation here. Again, you have to think they are worst case allocators. So they use as much memory as the peak memory used in your game. So that means that if you unload a level and create another one and use the same amount of memory for the same things, it's not going to allocate more memory. It's just like things just remain allocated there. So depending on the game, this usage may vary. But you have to think that this is like game specific. The main downside is that different areas are picked. If different areas are picked at different stages, the maximum memory use will be larger. This is a problem because if you use a game that uses a lot of something and then a lot of something else, then you're going to have like a worst case memory usage than if the memory shrinks. But this normally is not the case. Games are never that complex that do this kind of thing. And again, the benefits of doing this kind of growth-only allocation far outweigh the downsides. So this is okay. In the end, don't worry, this is just very efficient in the end, and it's generally the thing that most game engines use nowadays. Other game engines use things like stacks and things like that, but nowadays I think growth only is the simplest way to manage memory very efficiently today. So something that Godot does is paged allocators. So for example, this is a type of growth only allocator that allocates by pages. Like for example, you allocate something and it's going to allocate a page of elements. And if you need another element that surpasses this, it's going to allocate another page. It's again the same kind of thing, but growth only. And the advantage is allocating via like in pages is one that if you're just using the typical, I don't know, std vector and you resize and you increase the capacity, it has to move all the memory around to reallocate. Like it's going to resize the array, then it has to like allocate a new size and move everything there, and this is very inefficient. To avoid this kind of inefficiency, using paged allocators is very nice because you can allocate like big chunks that fit inside of like cages very, very nicely. And then you can like allocate more pages of that as you need, and you don't have to resize to allocate more pages. This is very useful. You have to keep a page list for like bookkeeping, but normally you have something called a free list that you can see in the graphic where you store which elements are free. So allocations and freeing things in page allocation it's extremely cheap. It's very, very cheap to allocate and free as you go, and it's totally fine. You may have a problem when you need to like create a new page because that's going to like probably lock a mutex or something like that. But normally it's fine. You're not going to have any problem with this. And finally, one interesting thing to understand about cage-friendly hash tables. We use open addressing, which is a very, very cage-friendly way of doing hash tables. Open addressing is very interesting. It has the downside that you need to have something called like you can only use like not all the occupancy. You have to resize if you reach like a percentage of the occupancy. Like if you are using 75% of the memory, then you need to resize and make it bigger. Because one problem with open addressing is that the data tends to be clustered around the memory. So when you're looking for an element that doesn't exist, if you have full occupancy, then it's going to go through all the elements. You need actual holes to happen around the clusters when you're looking for elements that don't exist. And for this, you always need to keep like, I don't know, 25% free of the occupancy. This is something that good to know. You're going to see that we are using open addressing a lot in Godot. And for that, we need to keep a bunch of memory free all the time. So we ensure that the clustering of the hashing leaves holes. So when an element is not found, it can return early and not just go through everything. One thing to understand about open addressing is that you really need good hashes with good distribution. We used to use like DJB2 for a lot of things. Bad idea. The distribution is terrible, and you would have like too much like cluster joining in the hash maps, and this would have really bad performance when looking for elements that don't exist. So we changed to Murmur 3, and this resolved pretty much. Now we don't really have this kind of like bottlenecks thanks to the hash maps. And again, the hash table is growth only still. Hash table you can reset, of course, and free the memory or just free the container. But while you're using the container, it's always growth only. You can't really shrink it unless you manually reset it. Okay, that's it. I hope it's clear. I hope you learned something about memory. This is going to make it easier for me to explain how the source code works when we discuss core in the next episode. So again, thanks lots for watching, and see you the next episode.